The question of whether 3I Atlas, for example, shows non-gravitational acceleration, that's still being calculated, debated.
The shock lands without warning. At the exact moment the December 13th, 2025 image resolves on astronomers' screens, something is wrong. The nucleus of 3I Atlas does not bloom. It does not smear. It does not soften under solar heat. Instead, it locks into focus like a hard point of light, sharp and compact, as if the sun's glare cannot touch it. This is not a subtle discrepancy. It is an immediate violation of expectation, and every trained observer sees it at once. Interstellar ice should be fragile here. As the object dives deeper into solar influence, heat is supposed to tear it apart, releasing dust and gas in a widening cloud. That is how comets behave. That is how physics has always behaved. But exposure after exposure keeps stacking. Minutes turn into hours, hours into more than 2 full hours of accumulated data, and still the nucleus refuses to spread. The light profile remains tight, controlled, unmoved. The sun is applying pressure in real time, yet the object responds as if the rules do not apply. At first, astronomers search for excuses: instrument error, tracking instability, processing artifacts. They rerun calibrations. They cross-check filters. They compare notes across observatories. The result is the same every time. The compact core is real. It is persistent. And worse, it has been there before. When archived observations are pulled, the same unnaturally tight nucleus appears again and again, stretching back months. This is not a momentary glitch. This is a pattern that has gone unnoticed until now. Alarm replaces curiosity. Databases of thousands of known comets are opened, their thermal profiles and brightness curves laid side by side with 3I Atlas. None match, not one. Every comparable object shows visible degradation under similar conditions. Dust halos grow, jets flare, nuclei soften. But 3I Atlas does none of this. It stays compressed, as if insulated from forces that shred everything else. The anomaly is no longer theoretical. It is measurable, repeatable, and happening now. This is the moment scientific tension spikes. The sun is not a suggestion. It is the dominant force in the inner solar system. When objects approach it, they yield. They always have. Yet here is something that appears to ignore that authority entirely. The language in internal notes begins to change. Words like unexpected give way to unexplained, then to incompatible. A quiet fear settles in, not of what the object is, but of what it resists. If solar heating cannot break it apart now, then what conditions would? Researchers acknowledge the most unsettling truth privately. This behavior is not predicted, not modeled, and not resolved by any known mechanism. This is not theory being tested. This is observation overruling expectation in real time. The sun is doing what it has always done. The object simply is not responding. That inversion alone is enough to force a reevaluation of assumptions that have stood for decades. And as the data continues to stream in, one question begins to dominate every discussion. If the nucleus refuses to yield to heat, pressure, and proximity now, what happens when something else pushes back harder? Because the images do not end here. And the next anomaly is already visible, forming in a direction no comet should ever point. It begins with a shock that ripples through observatories worldwide. A bright, narrow structure is clearly visible extending toward the sun, from 3Y Atlas, not away from it, toward it. The moment the alignment is confirmed, scientists freeze. Every known rule says this should be impossible. Solar heat and radiation are supposed to blast material outward, shredding ice and dust into a tail that streams away. Yet here, the sun is pushing with full force, and something is pushing back. Frame after frame removes doubt. The feature does not flicker. It does not bend with perspective. It does not vanish when Earth's position shifts. As the comet races along its path, the sunward structure remains locked in place, stubborn and precise. Perihelion passes, angles change, models update. Nothing breaks the alignment. What should collapse instead stabilizes. What should weaken instead sharpens. The realization spreads quietly at first, then fast. This is not an illusion. The fear deepens when physics is applied. Solar radiation pressure is calculated, measured, confirmed. It is immense, enough to strip typical comets bare, yet the inward-facing emission survives it continuously. That means energy is being supplied, redirected, or contained in a way no comet has ever demonstrated. This is not passive debris drifting on chance forces. It behaves as if it is being sustained actively. Confirmation arrives from multiple directions. Hubble's data agrees. Ground-based observatories agree. Independent teams reach the same conclusion without coordination. The signal remains sunward, stable, persistent, real. With every confirmation, one of cometary science's most trusted assumptions collapses. If material can resist the sun like this, then something fundamental is missing from current models. Then comes the detail that tightens the dread. The emission does not fade with distance. As 3I Atlas shifts farther from the sun, the structure does not weaken the way sublimation-driven activity should. It holds. That means heat alone cannot explain it. Pressure alone cannot explain it. Distance does not explain it. The list of explanations begins to thin dangerously. Researchers choose their words carefully, but the implication is clear. Something is sustaining the emission against solar force. Whether it is an unknown physical process, an extreme material state, or something never documented before, no one can yet say. What they do know is this. The closer the object gets to Earth, the harder it will be to hide the truth in low-resolution data. Telescopes are already retargeting. Exposure times are being adjusted. This is no longer routine observation, it is preparation. Because if this sunward structure survives closer scrutiny, the question will no longer be what is happening. It will be what is capable of doing this. And as attention shifts inward, away from the tail and toward the heart of the object, scientists realize the next images may reveal something even more unsettling, a nucleus that does not behave like a comet at all. The shock hits the moment analysts isolate the nucleus and realize something is fundamentally wrong. This is not a diffuse, fragile core struggling against solar heat. It is sharp, tight, almost engineered in how it holds itself together. Every new frame shows the same pattern. Energy is not spreading outward the way comet physics demands. Instead, it collapses inward, concentrating into a dense central point. The light profile drops off abruptly, as if the object is refusing to shed material. Dust loss is minimal. Gas release is muted. The sun is pouring energy into it, and the nucleus is not responding the way nature says it should. Scientists rewind the data again and again, expecting to catch the moment where heat finally wins. They expect blooming, cracking, or at least a softening edge. None appears. The core remains compact across wavelengths, across instruments, across weeks of observation. This is not a snapshot illusion, it is persistent behavior. At this distance from the sun, interstellar ice should be violently unstable. Instead, the nucleus behaves like a hardened point, absorbing stress without visible degradation. The realization is immediate and unsettling. This is not passive endurance. Something about the structure is actively resisting disruption. Language inside research teams begins to shift. Early comparisons to lanterns, embers, or icy pebbles are abandoned. The metaphors harden. The nucleus is described as pinpointed, focused, even beam-like. One analyst quietly notes that the brightness profile resembles a laser more than a burning rock. That word spreads, not as a claim, but as a warning sign that intuition has broken down. When scientists change metaphors, it means models are failing. And here, every standard comet model fails at once. Fear enters not because anyone is claiming intent, but because concentration implies capability. To remain this compact under solar stress suggests unusual surface chemistry, extreme tensile strength, or an internal structure never before confirmed in natural bodies. Some simulations propose exotic crusts. Others hint at phase states that should not exist at these temperatures. None fully explain the data. Worse, several models agree on one thing. A nucleus this concentrated should not survive this close to the sun without catastrophic change. And yet, frame after frame confirms it does. The unease deepens as time works against expectations. Instead of weakening, the nucleus remains stable. Instead of dispersing, it sharpens in definition. The sun has not forced compliance. Physics has not reclaimed authority. What should have been a brief anomaly is turning into a sustained condition. At this point, the danger is not what the object is doing, but what it is refusing to do. As researchers prepare the next round of high-resolution tracking, one question dominates every private discussion. If this nucleus can maintain such extreme compactness now, what other behaviors are still hidden? And with that unanswered, attention shifts forward because the next data set may not just show what the nucleus is, but what it is about to trigger next. The alarm triggers the moment trajectory data updates, not from a telescope image, but from numbers that refuse to stay still. Orbital calculations begin to drift by fractions too small for the public to notice, yet impossible for scientists to ignore. 3I Atlas is accelerating, but not in a way gravity can explain. This is not random wobble or rotational chaos. The motion is clean, directional, and persistent. The object is gaining speed along a defined vector, as if nudged by a force that should not exist in empty space. In control rooms and data threads, the tone changes instantly. This is no longer just something strange to look at. It is something that moves with purpose-like consistency. Researchers overlay the acceleration data with earlier imagery, and the connection snaps into focus. The unexplained motion aligns precisely with the sunward emission already defying physics. Two anomalies are no longer separate problems, they are part of the same mechanism. Whatever is producing the inward-facing structure is also altering the object's path. The discovery shifts from passive observation to active concern. Comets can experience non-gravitational forces, but only when outgassing violently and always away from the sun. This acceleration runs against that rule. It suggests internal activity, sustained output, and energy release that does not taper off. The fear deepens because internal activity means the object is not inert. It is doing something. As models update in real time, a disturbing implication emerges. The force appears strong enough to generate a faint, luminous wake, one that points inward, directly opposing solar radiation pressure. That configuration should collapse almost instantly. The sun should tear it apart, yet observation after observation confirms it remains intact, stable, persistent. Scientists hesitate to use loaded language, but the data forces uncomfortable comparisons. This behavior resembles thrust without calling it thrust. No jets flare visibly, no fragmentation occurs. The object simply continues, subtly accelerating as if balanced on a knife edge between physics and something unexplained. The realization lands hard. This should not be sustainable. Yet it is being sustained right now. The tension peaks as projections extend forward toward Earth's approach window. If the acceleration increases even slightly, current classifications will fail. If it remains constant, the mechanism behind it demands explanation. And if it sharpens, if the force grows stronger as proximity increases, then the behavior crosses a line from anomaly to active phenomenon. Scientists know the next data set will decide which future they are dealing with. Telescopes are already reorienting. Calculations are being rerun without assumptions baked in. Because as 3I Atlas continues its silent push through space, the question is no longer what is it doing, but what will it do next, as the countdown toward Earth continues. The briefing ends, but the tension does not. Observers replay NASA's November presentation frame by frame, and the danger becomes clear not in what was said, but in what was missing. No mention of the compressed nucleus. No acknowledgement of the sunward emission, no reference to the non-gravitational motion quietly appearing in the orbital data. The anomalies are not challenged, corrected, or explained. They are simply absent. In scientific culture, this kind of silence is never neutral. It signals uncertainty that cannot yet be controlled. Outside the official channels, researchers exchange messages in private threads and late-night calls. They recognize the pattern instantly. When data does not fit existing models, it stays buried in technical papers and raw archives, far from public summaries. This is not secrecy for drama, it is caution under pressure. But caution has a cost. Independent astronomers pulling fresh data from public servers see the same troubling features repeating. The sunward structure remains. The nucleus still refuses to diffuse. The numbers do not soften with distance or time. Fear sharpens when the timing becomes impossible to ignore. These omissions are happening weeks before 3I Atlas reaches its closest approach to Earth. Observation schedules are being finalized. Telescope time is being allocated. What gets priority now determines what can still be answered later. Some researchers realize that if the wrong assumptions guide these decisions, the best window to understand the object could be lost. The discovery shifts from the sky to the system watching it. Silence becomes the anomaly. If nothing is wrong, why avoid the subject? And if something is unresolved, why risk waiting? The tension peaks as astronomers understand the next images may force the issue into the open, whether agencies are ready or not. Because once higher resolution data arrives, omission will no longer be an option. And when that happens, the conversation will change fast. The danger is no longer theoretical. On December 19, 2025, 3I Atlas reaches its closest distance to Earth, and every decision made by astronomers now carries weight. What they see is already outdated the moment it arrives. Each photon hitting a telescope left the object 15 minutes earlier, meaning the comet is always ahead of human awareness. If something changes suddenly, if the structure collapses, ignites, or accelerates, it will already have happened before anyone can react. Across the globe, observatories shift into emergency precision mode. Instruments are recalibrated mid-session. Exposure times are shortened. Filters are swapped in real time. This is the narrowest observational window scientists will get, and they know it. At this distance, normal comets should flare violently or begin to fall apart. 3I Atlas does neither. The nucleus remains tight. The light profile stays sharp. The sunward emission does not weaken. It holds. That persistence is what unsettles the room. If the emission survives this approach, it means solar pressure is still failing to overpower it. That breaks a rule scientists rely on. Radiation pressure should dominate here. Heat should destabilize surface layers. Ice should erupt outward. Instead, the structure remains organized, directional, and controlled. Models begin to diverge sharply. Some predict imminent sublimation, others predict fragmentation. A growing number predict nothing at all because the equations stop producing answers. The tension spikes when new frames arrive and show no dramatic change, no outburst, no collapse, no thermal bloom. The object behaves as if it anticipated this distance and prepared for it. That is not a claim of intent, but the resemblance is hard to ignore. The data does not scream catastrophe, but it refuses to calm anyone down. Behind closed doors, scientists begin to ask the question they avoid saying aloud: what if neither explanation fits? What if this is not rapid sublimation, and not dormant survival, but something else entirely? A rare physical state, an unknown interaction, a behavior never recorded because nothing like this has ever been observed so close, so clearly, and so wrong. As December 19th unfolds, telescopes stay locked on target. The margin for interpretation narrows by the hour. Either the object finally obeys the sun, or it proves decisively that it never intended to. And when the next data set arrives, it will determine whether this encounter ends as a solved mystery or becomes the beginning of a far more unsettling chapter.